Welcome to this next video in the playlist on ring theory. In this video, what we're going to talk about is evaluating polynomials at polynomials. Okay, so this video is intended to follow the previous video in the playlist on ring theory entitled Evaluation Homomorphisms for Polynomial Rings. And indeed, what we're going to study in this video is really just a generalization of what we saw in the previous video. So we're going to explore another extremely important homomorphism where the domain is a ring of polynomials. Okay, so let's start off with the setup then. We're going to be working with a ring of polynomials, so we need a ring of polynomials to start off with. So we'll take the ring of polynomials over some ring, capital R, where of course, as usual, we're assuming that this ring is a non-zero commutative ring. Okay, so we generate the ring of polynomials for some non-zero commutative ring, capital R, and now we're going to be working with this ring of polynomials here. Okay, right. So now what we're going to discuss, or what we're going to introduce, or define, if you like, is the evaluation homomorphism for this ring of polynomials over the commutative ring capital R, where we evaluate each polynomial at a polynomial. Okay, so in order to define this, we need to have some polynomial that we're going to evaluate all other polynomials at. Okay, so you need to start off by picking some polynomial. So we'll call this polynomial p of x. So you pick some polynomial which I'll call p of x from the ring of polynomials over the ring capital R. So first of all, pick p of x. Okay? Now, I'll assume that you have picked some polynomial, and let me stress you can pick whichever polynomial you like. Okay, it can be a constant polynomial if you like, and indeed if it is a constant polynomial, then what we're doing here will become what we did in the previous video, but the new thing here is that you can pick some non-constant polynomial as well. Okay, you can even pick the zero polynomial, whatever polynomial you like, pick whichever one you want. And now what I'm going to do is define the evaluation homomorphism for this polynomial p of x, so I will subscript phi with p of x. So the homomorphism, we usually use the symbol phi for homomorphism. Again, because it's pertaining to the polynomial p of x, it's about this polynomial p of x, it's defined using this polynomial p of x, we will subscript it p of x. So the evaluation homomorphism for p of x, and it's going to be a mapping from the ring of polynomials over the ring capital R, so it's going to have as its domain the ring of polynomials, so it's going to map every single polynomial in here onto something. And what's it going to map it onto? Well, this time it's not going to be the ring capital R, it's going to be more general, it's going to be the ring of polynomials over the ring capital R. So in fact the domain and the codomain are exactly the same in the case of this mapping here. Now, it's going to be a homomorphism. Okay, so we've got a homomorphism between the domain and codomain, which are the same ring. Now there's a special word for such a homomorphism where the domain and codomain are the same ring, and we call it a ring endomorphism. And of course the word endomorphism, like the word homomorphism, can also be applied to groups or vector spaces or fields or whatever. Okay, of course we're talking about a homomorphism between two rings, so this endomorphism will also be between two rings, so we could call this a ring endomorphism. Okay, and you might ask, well, what's the difference between a ring endomorphism and a ring automorphism? Well, a ring endomorphism doesn't need to be a bijective map, and in general, the evaluation homomorphism pertaining to a polynomial p of x is not going to be a bijective map, although it is going to be a homomorphism. Okay, an automorphism, if we describe this as a ring automorphism, that would imply that it was a bijective map. Okay, it was a ring endomorphism that was bijective, so ring automorphism is slightly more specialized. Okay, so this is going to be a ring endomorphism, although we will often just refer to it as a ring homomorphism. That's really just to introduce you to another piece of fancy terminology. Okay, so I will still call this just the evaluation homomorphism rather than endomorphism. Okay, right, so this doesn't tell me much yet. I haven't actually defined how this is going to work, so let me now define exactly, make precise how this is going to work. So it's going to take any polynomial in here, okay, and the polynomial in here will look like this, the sum over I of ai xi, okay, where of course all the ai's are from the coefficient ring, capital R, and we're going to map this polynomial onto the sum over I, and now we're going to stick in for the x's p of x. So it's going to become ai, and I'm actually going to put a multiplication symbol in there, and I'll justify why I'm doing that in a moment. Okay, it's just to stress a point. And then we'll have p of x to the power of I. Now I want to now completely stress how different this thing is to this thing. Okay, remember over here, this was just an abstract symbol. Okay, the powers of x were just placeholders. Okay, you just had x with a certain natural number above it. Okay, then all you've done is stuck some coefficients from your ring capital R in front of these funny symbols, these powers of x, but it didn't mean anything, it was just a symbol. And then in between the different terms, you put these plus symbols, and again it didn't mean anything, it was just a symbol, you were just creating these funny symbols. Okay, and that of course is the formal sense of what the ring of polynomials as a set fundamentally is. It's just a set of symbols that once you've defined what the set of symbols capital R is, you can create the set of symbols for the ring of polynomials. You don't actually need this to be a ring in order to create this set of symbols. For any set you can create this set as well. Okay, of course it won't end up being a polynomial ring, you won't be able to define the addition and multiplication in a beautiful way, but you can create it as a set of symbols. So on this side, this was just an abstract symbol. On this side, the meaning is quite different, and that's why I've stuck this multiplication in to stress that. Okay, now everything is actually talking about the addition and multiplication in the actual ring of polynomials. So the addition now becomes addition in the ring of polynomials, whereas here it was just a symbol. Okay, it just meant have these terms with these plus symbols in between, whereas now you need to think about the plus symbols in between the terms as actually being the addition law defined on the ring of polynomials. Okay, so in a way this isn't the actual answer on this side, this is how to get the answer. There's still a lot of work to be done here. You have to actually do some arithmetic in the ring of polynomials over the ring capital R to work out the final answer. This is an actual element of this set. This is a whole bunch of operations telling you how to get an answer back in the actual set. Okay, so you must think of this as summing in the ring of polynomials over the ring capital R. So whenever I colour something in orange from now on, it's going to mean that it's an operation in the ring of polynomials in the ring capital R. And in green, we will denote green the abstract symbolic plus and sticking a coefficient in front of it. Okay, so this is symbolic if you like. This is just the cold, hard symbol. Okay, whereas this is operations in that ring of polynomials to arrive at the final answer, which will just be a cold, hard symbol. But this, at the moment, I'm not telling you the actual cold, hard symbol that is the answer to this. I'm telling you how to work out the cold, hard symbol by adding lots of these monomials together, or rather not monomials necessarily, but lots of these different polynomials together in the ring of polynomials over the ring capital R. Okay, in addition, this is now actual multiplication. You are multiplying a constant polynomial. AI is a constant polynomial in the ring of polynomials, so in a way that's changed its meaning now. We're thinking of that as being a constant polynomial in here, so I might even underline that in orange. It's changed its meaning from just being a cold, hard coefficient in front of a placeholder, which was an element of the ring capital R, to now actually being some constant polynomial in here. And then we've got the polynomial p of x, which is some polynomial, and then it's being raised to the power of I, and now the raising to the power of I is again done in the ring of polynomials. That means take this polynomial p of x and multiply it with itself I times according to the multiplication law in the ring of polynomials over the ring capital R. Then multiply it with this constant polynomial, do this for each one of these i's, and then sum them all up in the ring of polynomials. If you do all of that, you'll get a cold hard answer, which is an element of the ring of polynomials over the ring capital R, and that will then be your answer. So this isn't the final answer, this is telling you how to construct the final answer. But I hope it's a reasonably intuitive definition for what this polynomial evaluated at p of x is going to be. Okay, but I do want to stress how different this thing and this thing actually are. Okay, so hopefully you can appreciate that this mapping is not in general going to be a bijective map. Okay, so you can appreciate that this usually is not going to end up being an automorphism, so we do need to call it a ring endomorphism. Okay, in particular there will be cases where it's not going to be surjective, where you can easily imagine the case where there are certain polynomials here that there is nothing over here where if you evaluated that p of x it's going to give you the answer over here. Okay, so just to make this absolutely crystal clear, what I want to do is do a concrete example. Okay, so we will take as our ring of polynomials the ring of polynomials over the integers. Okay, and we'll pick our p of x, so the polynomial we're going to use to evaluate all other polynomials at. We'll pick x squared plus 2, a perfectly nice polynomial in the ring of polynomials over the integers. Okay, and now let's apply the evaluation homomorphism pertaining to x squared plus 2. Okay, and I could even put x squared plus 2 down here in the subscript to some other polynomial in the ring of polynomials over the integers. Okay, so let me just devise some other polynomial. Let's have x cubed plus 6. So I'll do a nice simple one. Okay, so how am I going to do this then? Well, what I'm going to have to do is just apply the definition here, and of course I'm going to stick x squared plus 2 into the x cubed here. Okay, so this is going to become x squared plus 2, and now I want to cube that in the ring of polynomials over the integers, and then I want to add 6 onto it, where this addition is now in the ring of polynomials over the integers. So the taking to the power and the addition there, they are now in the ring of polynomials over the integers. Okay, so let's firstly multiply x squared plus 2 by itself 3 times. Okay, so this is a little bit like hard work, but let's do it anyway. So we'll firstly multiply x squared plus 2 with x squared plus 2, and then we'll add another one on there. So let's just do this. Okay, so x squared times x squared will give us x to the power 4, plus 2x squared will give us plus 4x squared, and then we'll get plus 4 as the final thing, and then we'll need to multiply that by x squared plus 2 again. So this will be x squared plus 2, and of course I'm applying multiplicative associativity here, so if you want to work this out you can split it into multiply these two first together and then multiply it with this one, and we know that it really does not matter which order where you put the brackets, so I'm using that fact implicitly here. Okay, so let's now multiply these two together. So we'll have x to the power 4 times x squared, which will give us x to the power of 6, plus 2x to the power of 4, but we'll also get an x to the power of 4 by multiplying this one and this one together, so we'll get 4x to the power of 4 there, so we'll add those together, so we'll get plus 6x to the power of 4. Okay, so now what I need to do is multiply this one with 2, so I'll get 8x squared. Okay, but then, of course, when I multiply this one with this one, I'll also get a power of x squared, so we'll have plus 4x squared there, so add those two together, so we'll get plus 12x squared, plus, and then finally we'll have plus 8, but then we need to add on plus 6, so that will become plus 14. Okay, so here then is the polynomial, the final answer in the ring of polynomials over the integers to what the polynomial x cubed plus 6 evaluated at the polynomial x squared plus 2 is actually going to equal. Okay, so if this wasn't clear before, I hope it is clear now that we've done a concrete example. Okay, so what I now want to do, actually just before I go any further, what I want to point out is how this is just a generalization of what we looked at in the previous video, and then of course we need to prove that this is indeed a homomorphism. Okay, right, so firstly then, showing you that this is just a generalization of what we looked at in the previous video, well of course you could pick as your polynomial p of x a constant polynomial or the zero polynomial. Okay, if you did that, then you would just be sticking in for x a constant polynomial or a zero polynomial. Okay, and that would be exactly what we've been talking about in the previous video. Okay, where we discussed the evaluation homomorphism for a polynomial ring. Okay, and of course it would still be mapping you onto the ring of polynomials, but it would be mapping you onto a specific subset of the ring of polynomials, which is the constant polynomials, i.e. The actual coefficient ring capital R. So we can always view the coefficient ring as being a proper subset, or a proper subring even, of the ring of polynomials over that ring capital R. And indeed, if you pick as your polynomial a constant or a zero polynomial, then this map will certainly not be surjective. It will just be mapping you onto this subring of the ring of polynomials. Okay, but that's why we can view this as a generalization of what we did in the previous video, because if you pick your polynomial as a constant polynomial or the zero polynomial, then you're in business. Then it is exactly what we talked about in the previous video. But now we have the option of picking a non-constant polynomial, which is the new stuff. Okay, right, so what I want to do now then is prove that this is indeed a ring homomorphism. So we need to prove additive compatibility, multiplicative compatibility, and that the multiplicative identity here is mapped onto the multiplicative identity here. Okay, well the final of those should be really easy, but let's start with additive compatibility. Okay, so additive compatibility. So what we want to prove is that if we take phi for p of x, and I might soon drop the p of x here because it's just annoying having to continually write that, of two polynomials added together, so of the polynomial a of x added to the polynomial b of x, and that is some answer in the domain. Okay, so if you firstly add these two polynomials together in the domain a of x plus b of x, and then apply this mapping, I want to show that you get the same answer as if you firstly map them into the codomain. So if you take phi p of x, and I do really want to drop that p of x because I'm struggling with what to say. Okay, phi sub p of x of a of x, I suppose I could call it, plus phi sub p of x of b of x. Okay, I want to prove that indeed this is the same thing as this, that the answer is the same, that you can either firstly map the two polynomials a of x and b of x into the codomain and then add them together there, or you can add them together in the domain and then map them into the codomain. Okay, so these additions here, they're additions in the ring of polynomials over the ring capital R. Remember, the domain and the codomain are exactly the same ring, so the addition is going to be the same. Okay, I'll just write out my ring of polynomials over the ring capital R once again and underline it in orange to remind you that all operations in there are going to be coloured in orange. Okay, right, so this is what we want to show. It's not been proven yet, so I'll put a little question mark there. And I've taken the executive decision that I am going to drop writing the p of x because it is just awkward. So we'll now just call our evaluation homomorphism phi, but of course it hasn't changed. It still is specific to some polynomial that you have chosen to evaluate all other polynomials at. It's just I can't be bothered to actually continually have to say phi sub p of x of a of x. Okay, so let's try and prove this statement then. So we'll start off with the left-hand side, we'll develop it a little bit, we'll then move over to the right-hand side, develop it a little bit, and show that the two things are equal to one another, the standard approach to something like this. Okay, right, so let's start off with the left-hand side here. So the first thing to do is actually write out these polynomials a of x and b of x explicitly. Okay, so this becomes phi of, and now I will write the polynomial a of x out as the sum over I, ai x to the I here, and then it will be added to the polynomial b of x, and I'll write b of x out as the sum over I, bi x to the I, like so. Okay, and that addition there is still in the ring of polynomials with coefficients in the ring capital R. So this is just me writing a of x out explicitly, and this is just me writing b of x out explicitly. Okay, now I know how to add these two polynomials together. You just do it by adding the coefficients together that are in front of the same powers of x. You do it component-wise. Okay, so I'm going to color code this in, so we'll have operations in the ring capital R denoted in purple. Okay, so this is going to become the phi of the sum over I of ai plus bi x to the I. Okay, now this addition here is addition in the coefficient ring, capital R. And by the way, these sums here, these are still just symbolic sums. Okay, if you like, of course, you can view it as the monomial decomposition, but you don't need to. You can still view it as the cold, hard, symbolic sum. Okay, so just creating the polynomial, and this is just adding the coefficients that are in front of the same placeholder basically together. So at the moment we do not need to think about changing this from being a symbolic sum to actually being a real sum in the ring of polynomials over the coefficient ring capital R. Okay, right. Now, of course, all that's about to change when we take phi of this. So now let's just apply the definition for what phi of this is going to be equal to. Okay, so phi of this is going to be equal to, now we just apply the definition, it's going to become the real sum, the sum in the ring of polynomials, and we'll have the coefficient ai plus bi here, okay, and then it will be multiplied by the polynomial p of x to the power of I. Now, there's one thing that I want to stress here. I coloured this in purple here because in the cold, hard sense, where you're actually defining addition in the ring of polynomials, then yes, you have to think about just adding the coefficients in the ring capital R. But now that we understand how to add polynomials in the ring of polynomials, what we can think of this as actually being is the sum of the two constant polynomials in this ring of polynomials. Okay, so it is going to be helpful now to change that addition from being purple to being orange. Okay, this multiplication is now multiplication in orange. It's the multiplication of this constant polynomial with p of x to the power of I. You are taking p of x to the power of I in the ring of polynomials over the ring capital R. And this sum is also summation in the ring of polynomials. So I want everything to be in terms of operations in the ring of polynomials. And now that we've got a good understanding of how addition and multiplication work in there, and of course I can now just think of this as being addition of those two constant polynomials in the ring of polynomials, and it's helpful for me to now, instead of thinking about it as addition in there, think about it as addition in there. Of course, addition in here is isomorphic to addition of the constant polynomials in here. Okay, this is truly included in here, so there is an injective ring homomorphism from here to here, okay, which is just the inclusion map. So truly you can just change those additions like that. Okay, once of course you know what you're doing. Right, so now is probably the point where we need to develop the right hand side a little bit and hope that somehow we turn it into this. Okay, so let's start off with the right hand side then. So applying phi to a of x, of course, really we need to have the same intermediate step as here, where we firstly write in for a of x and b of x, them written out explicitly, and I will just include that, why not? So this will be phi of the sum over I, ai, x to the I, and of course this is still just symbolic, okay? So this sum just means create that symbol. This is just telling you how to create a symbol, basically, where you're putting plus signs in between all of the terms. And on this one here, whoops, missed out the phi. How am I going to correct that? I'll just start again. Phi of the sum over I, bi, x to the I. Okay, so I've just written a of x out explicitly like so, and written b of x out explicitly like so. And this addition, of course, is still addition in the ring of polynomials. Okay, now let's apply phi to this polynomial and phi to this polynomial here. Okay, and what are we going to get if we do that? Well, if we apply phi to this polynomial, then it will just become the sum over I, and that's a real sum, of course, the constant polynomial a of I times the polynomial p of x to the power of I. So everything's changed meaning. This is a real sum now in the ring of polynomials. This is a multiplication in the ring of polynomials. This is taking to the power of I in the ring of polynomials. And then now we're going to put another addition there, which is still an addition in the ring of polynomials, and we're going to be adding this. Okay, so we'll have the sum over I of bi, the constant polynomial bi, times the polynomial p of x to the power of I, and again everything's got this new meaning. So the addition is in the ring of polynomials, the multiplication is in the ring of polynomials, the taking to the power of I is in the ring of polynomials. Okay, so I've got a huge, great big sum then of these sort of terms in the ring of polynomials over the ring capital R. Okay, so what of course I can now apply is the fact that addition obeys associativity and commutativity, so I can move everything around nicely, and I can bring things that have the polynomial p of x to the same power of I together. Okay, so if I've got something over here which is p of x to a certain power of I, and something over here which has p of x to the same power of I can arrange it so that they are next to each other, and then I can apply the fact that multiplication distributes over addition to factor out the power of p of x, and then I'll just get the coefficient ai plus the coefficient bi, and of course that just turns this into this. Okay, so that is how I can complete this beautiful loop here, and how I can conclude that yes, indeed, this equals is true. Additive compatibility holds. Okay, so that's excellent. This mapping does indeed obey additive compatibility. Okay, with this mapping, addition here is compatible with addition here. Okay, so we will have a break here, and in the next video we will do a similar proof for multiplicative compatibility, and then we will do a one-line statement of the fact that the multiplicative identity is mapped onto the multiplicative identity, and hence we will have concluded that this mapping, this evaluation at a certain polynomial, is indeed a ring homomorphism.